Today I'm going to dispel one of the myths about water pressure. And imagine that you're trying to wash your car or wash a window on your house, for example. Okay, and you're trying to spray your car. So you have to imagine that this is the hose. And a lot of people think that if the water is now running out of the hose, and what most people do is they'll take their hand and they'll put their finger over the end of the nose right here, or the nozzle or the opening, and what it's going to do is it feels like it's creating this massive pressure that you can now spray off all the debris off your window and all the bird poop and everything that's there, or whatever it is, whatever it may be. The idea is that when you cover it like this, you're decreasing the opening, and so you're increasing the pressure of the water that's coming out. Actually, when you do this, you're decreasing the water pressure. So what's actually happening? Why does the water pressure go down when you cover it like this? This is all related to what's called Bernoulli's principle. So this is section 13.1, number 3. So let's do this scenario, and let's draw the opening of this container or like a hose. So imagine that this is going to be the opening on one end, and here's going to be this container or cylinder, and the water flow is going to be moving in this direction. So this is the one end, and what we're going to do is now we're going to narrow this down. So imagine that you have placed some type of nozzle on top of your hose. Okay, so here's the nozzle that you've just placed on top of that. You can try to make it three-dimensional like this. And let's say that it has this extension like this. So what we're going to do is we're going to follow the path of a disk of water. So imagine we're pushing the water through this, and here is this small sliver of water. Okay, so here's the water. I've drawn it as if it were a solid, but we know that this is a liquid. So here's the water, and the water is traveling through this container, this hose. So it's traveling at a velocity, and it's traveling in this direction. So here's the initial velocity. Okay, so it's still traveling along. When it comes here, it's still going to have the same velocity. So the velocity of the water here is going to be the same as the velocity of the water here. It's the same dimensions of the hose. But now what we have is we have this narrowing down, and we're going to now have to push this cylinder into this smaller container. So in this zone right here, we have the same volume, this disk. So we have the same volume of water is going to move through. So the same volume of water has to move through this opening right here. Well, all of this water is going to get squashed, and it's going to get pushed out through here. So what happens is it actually increases the velocity. So the velocity is going to increase in coming out of this opening over here. So let's take a look at the kinetic energy in this scenario. So here we have K1, here's the kinetic energy, and here we have the final kinetic energy. Okay, so if you remember, K is equal to 1/2 mv squared, so we have 1/2 mv squared, and now we have 1/2 mv squared for this as well. But if you take a look at the final volume, here's the initial volume here, here's the final volume here. Okay, so it's the final volume. And since we've increased the the velocity, we're increasing the kinetic energy. So if we're increasing the kinetic energy, some positive work has to have been done on the water. So the water is flowing along at a certain velocity. Now this column of water is going at a larger velocity. So we have positive work that is being done on the water to increase the velocity. So you can't get something from nothing. We just can't all of a sudden have an increased velocity with an increase of work being done. That has to come from somewhere.